Well,
Okay. I think we should just get started and see who else trickles in. So I'm absolutely delighted to present Viraj Pandya, the Hubble Fellow at Columbia, but before that, a graduate student at UC Santa Cruz and a very active JWST collaborator in many different collaborations. So he spans the theory and observational side, and I've had the pleasure of working with him as part of Sears, as did Aaron. So we are very keen to hear what he has to say, but also with the context of habitable worlds that's on the horizon. So I'm absolutely keen to hear from Viraj and absolutely delighted that he's here. So thank you, Viraj, and would you take it away?
great. Thank you so much, Fene and Aaron, for the introduction and for the invitation. It's great to be here. So I'm going to try to convince you in this talk that there is an interesting and important unsolved puzzle about the 3D shapes of high redshift star-forming galaxies, including high redshift Milky Way progenitors. And I'm going to try to make the case for how Habitable Worlds Observatory, say 20 years onwards in the future, can contribute to this kind of important science. So I'll start with a brief history of the problem, along with a review of some recent JWST results, and then I will speculate on some likely advances that we might see with JWST over the next few years, as well as with the Roman Space Telescope, and then with the extremely large ground-based telescopes in the 2030s. And then near the end, I will say some words about how I might use Habitable Worlds Observatory to address this kind of science. So I like to start with this nice quote from Edwin Hubble's 1926 APJ article, almost 100 years ago now, where he says that there are many more galaxies nearby that appear round or nearly round in projection than can be accounted for by randomly oriented disk-shaped objects alone. And of course, as we all know, this is one of the many properties that he used to then justify his development of the Hubble tuning fork diagram, where he proposed that there's actually a new class of intrinsically round elliptical galaxies seen on the left part of this Hubble sequence. And we kind of take it for granted now, but really it took decades of work by many astronomers to establish that this Hubble sequence, at least at low redshift, is also a 3D geometry sequence in the sense that the ellipticals in many cases are actually round in 3D, and then the spirals on the right are like flattened pancakes. So many years later, of course, with the launch of the telescope named after Hubble, which is only a few months older than I am, there were a lot of great discoveries. And one of the most exciting things in the first few years, in my opinion, is that in some of the early deep fields, astronomers identified very elongated and in many cases clumpy blue star-forming galaxies of high redshift that they called chain galaxies. And this was, you see some examples of these here. This was studied by many astronomers. So for example, the Elma Greens in the mid-2000s had this nice paper where they show that, yes, if you look in Hubble imaging close to the detection limit, you start to see that there's many linear looking galaxies that dominate the population of high redshifts in the star-forming regime. And NASA Cosmic Origins Deputy Chief Scientist Swara Ravindranath herself had a very nice paper in the mid-2000s showing that the ellipticity distribution of high redshift star-forming galaxies in the solid line here is in fact biased towards more elongated systems. And that's very different from the ellipticity distribution of low redshift systems, which is more uniform, as shown by the dotted line here. So all this stuff, this early work was probing the rest frame UV morphology of these high redshift galaxies. And there were always concerns, maybe you're probing like a biased tracer of the underlying galaxy morphology with these UV bright H2 regions or star-forming regions. And so with the installation of the WIF-C3 camera on Hubble, which opened up near-infrared imaging, as well as the completion of large surveys with Hubble like candles and 3D HST, there was this very nice paper in 2014 by Arjen van der Wel, who showed that indeed now in the rest frame optical, not rest frame UV, rest frame optical, these high redshift star-forming dwarfs had projected axis ratio distributions that were indeed biased or asymmetric, biased towards elongated values, and that this was very different from the axis ratio distributions of low redshift star-forming dwarfs, which do not preferentially appear elongated, and also very different from the axis ratio distributions of massive galaxies at any redshift, which also do not preferentially appear elongated and instead have a uniform distribution of axis ratios. So there are many explanations for this, and one of the original ones, maybe the safest ones, is to say, well, look, we do see low surface brightness disks in the local universe, some of which are clumpy, and maybe all of these elongated galaxies that we're seeing in high redshift are just the edge-on views of some of these high redshift, low surface brightness objects. And you're not seeing the round circular ones because you're not as sensitive to them. There's an incompleteness or surface brightness detection bias. This was bolstered by some hydro simulations later on, which did predict the existence of clumpy star-forming disks and argued that the edge-on manifestations would be easier to observe and detect compared to the face-on views. So this is one side of the argument. There's another camp on the other side that says, wait, there actually might be some intrinsic 3D geometrical evolution in terms of the high redshift, low mass star-forming population. And in particular, that these high redshift galaxies at low masses may actually not be axisymmetric circular disks, and instead they have a significant additional flattening along a second axis in 3D, so that in 3D they actually look like cigars or like surfboards, like oval disks or like these prolate ellipsoids. And so this is rather exotic, but it's actually not that crazy, because in the local universe we observe structures that are heavily flattened in along the second axis. We call them stellar bars, right? So in the local universe, we think the majority of disks have stellar bars. We observe this. Now, the problem with the high redshift systems is that we don't always see an obvious bright, aka massive, underlying self-gravitating disk out of which bars can form in high redshift systems, due to secular bar instabilities, for example. But there are other ways to form these kinds of very triaxial or prolate bar-like structures, and one of those ways is mergers. So there are some cosmological simulations that predict the existence of these elongated galaxies. It requires high resolution to probe into this high redshift, low mass regime. And the story from these simulations is that these galaxies are elongated because they live in dark matter halos that are themselves elongated in the same direction. And this entire system lives in a cosmic web dark matter filament that dictates the flow of mergers and gas along a preferential direction, which then helps stabilize the elongated shape of the galaxy in a particular direction. If this was true, then I wrote a paper in 2019 suggesting that maybe we should expect to see strong intrinsic alignment signals at high redshift for these elongated systems, because maybe they trace out filaments of the cosmic web. So this is very exciting, and I think we'll make a comeback in a few years with the launch of the Roman Space Telescope, which I'll say a little bit more about later. But in the meantime, I want to just stop and I want to say that it's been 30 years, and I don't think that anyone has a definitive explanation for why high redshift dwarfs preferentially appear elongated in the rest frame optical. And in this talk, I'm going to try to convince you that there is a smoking gun way to differentiate between these different scenarios. And I think Habitable Worlds and the ELTs will be able to do that. So I got excited a few years ago with JWST, and in particular in 2022 and 2023, because there were all these very exciting papers that showed convincingly that JWST was picking up disks where HST just completely missed them. So here's a nice paper by Dan Eisenstein showing one of these examples. There was a nice paper by Brant Robertson, which also showed identification of new disk-like systems that were missed by HST with its shallower imaging. And then I think one of my favorite figures from 2022 is this figure by Ferreira et al., which shows that the disk fraction in HST is dropping dramatically towards high redshift, but then the JWST disk fraction is much higher. at like the 40 to 50% level, which is amazing. So I got excited because I thought, oh, maybe JWST has found a lot of the face-on disks, and maybe it's definitively, ruled out maybe the 3D geometrical evolution scenario. But then we started asking this question, well, so yeah, JWST has detected a lot more disk-like objects that were previously missed by Hubble. But it kind of begs the question, how do you define a disk, right? So it's common practice, for example, to use visual classifications of individual galaxies one at a time, or to look for galaxies at high redshift that have exponentially decaying surface brightness profiles, like we see for local disks. But we wanted to go in and also get at this problem from a different complementary angle, a more statistical modeling angle. And so I'm lucky to be part of one of these early release science teams known as SEERS. And in fact, I got lucky. I got involved with SEERS as a first-year grad student at Santa Cruz as an astrophysical leadership fellow, where I got to actually shadow Steve Finkelstein, the PI of SEERS, as he was putting together this collaboration before it even got its name. So very lucky to be part of this. And so the SEERS team and I went in to the SEERS imaging, the JWST imaging, and we essentially fit every galaxy in the imaging with an ellipse, which comes from the Sursuch 1D Sursuch or 2D Sursuch modeling. And so then we characterize every galaxy by the projected axis ratio of its best fitting ellipse from the Sursuch model. And then we did a simple counting exercise where we asked, well, for galaxies of a fixed mass and fixed redshift, what does distribution of projected axis ratios look like for star-forming systems in the rest frame optical? So using redder filters for higher redshift systems. And when we did this, we saw that actually, even with the improved sensitivity of JWST, it's still picking up many more elongated galaxies compared to rounder circular ones in the high redshift, low mass regime. Again, star-forming population, rest frame optical morphology. So we then wrote this paper, which had this sensational title, Galaxies Going Bananas, but the title has a specific meaning. There's a meaning behind the analogy. So the reason for the title is that we don't only look at the 1D distribution of B over A, we look at the 2D joint distribution of B over A as a function of size. And when you plot galaxies, for example, in some high redshift, low stellar mass interval on this kind of diagram, they trace out a particular shape on this diagram. So at a fixed mass, fixed redshift, and then fixed size, especially larger sizes, galaxies are preferentially appearing with low B over A edge-on axis ratios, and there's a deficit of rounder, higher B over A objects. And so this shape looks to us like a banana. And so that's the inspiration for the title of the paper, Galaxies Going Bananas. And so here are some example images of some of these elongated systems. They consistently look flat and elongated. In some cases, they're clumpy, like the old chain galaxies from 30 years ago. And our main point is just that these edge-on systems are way too numerous compared to like the face-on rounder systems, which implies that if you want to preserve isotropy, not all of these edge-on systems can be just normal circular disks seen from the side. And so you may have seen a few weeks ago, the front page of the New York Times had this nice article by Dennis Overby, which he called "The Early Universe May Have Gone Bananas." I think it's a great title. There was a nice Columbia YouTube press release with a video of me kind of leaning into the banana analogy. And then there was a NASA press release last week with a nice beach-themed analogy involving pool noodles and surfboards and frisbees and volleyballs and so on. So very exciting stuff, but you have to be careful with this kind of analysis because of selection effects. And in particular, the one that we have known for a long time, as I mentioned at the beginning of my talk, that face-on disks are harder to detect compared to edge-on disks. And so you have to be very careful when you draw these kinds of conclusions. And so the way that we got around this, or that we addressed it, is we asked this question, well, is this deficit of rounder galaxies to the top right of the banana, is that deficit of round dwarfs at high redshift real? And we think it's real because we injected fake disks into our real Sears imaging with a range of sizes and magnitudes, aka surface brightnesses. And then we ran that imaging through our source detection pipeline, and we quantified our detection limits. And we showed that if there were large face-on disks down to stellar masses of 10 to the 9, out to redshift 8, then we should have seen them, but we didn't see them in Sears. And so we have to interpret this now. And so the interpretation is, for the interpretation, we'll start by approximating galaxies as different kinds of 3D ellipsoids. So here are some example extreme cases: a spheroid on the left, an axisymmetric or circular disk in the middle, and then one of these cigars on the right. So a population of each of these kinds of ellipsoids is going to leave a unique signature on that B over A versus size diagram. So take, for example, spheroids. No matter which way you look at them, they're going to appear round in projection, and so they're going to show up near the top of this diagram with high B over A values. Disks are different because you're equally likely to observe them from any viewing angle, and so they're going to show a uniform distribution of B over A, a vertical stripe in this diagram, at the location of the typical size in 3D, and then some scatter when you have a population of these things. The third class of prolate ellipsoids are fundamentally different because they have two short axes. This means that you're much more likely to observe these things with the long axis in projection, and very rarely you'll see these things directly down the barrel when they look like a small circle on the sky. And so on this diagram, a population of prolate ellipsoids will actually end up preferentially having large size and small B over A. And so again, if you look at this diagram on the right, the shape that it reminds us of is that of a banana. And so that was, one of our conclusions, that maybe, what we're seeing in the observations is a new class of intrinsically elongated galaxies in 3D. And so to actually, make this case, we wrote a hierarchical Bayesian model, which essentially takes millions of different types of 3D ellipsoids and their corresponding probability maps like these, and then just does a weighted sum, finds the optimal weighted sum to then reproduce the observed histogram of B over A versus size. And I'll skip all the details of that. I'm happy to talk about it if you want to, but I'll get to one of the punchlines, which is probably one of the most important questions: how common are these elongated galaxies? And so here I'm showing you a nice bar chart visualization. So the redshift evolution for two mass bins, in terms of the prolate or nearly prolate fraction in blue, the oblate fraction in orange, and then the spheroid fraction in green. And you can see that above about redshift 1, especially for the low mass population, the prolate or nearly prolate systems are just dominating at the 50 to 80% level. So this is not a rare population. This may be the dominant population. And then something else I'd like to point out in this diagram is that all of these redshift mass intervals were fit independently. They don't talk to each other. And so it's interesting that towards low redshift in both panels, we start to see that the contribution of the axisymmetric circular disks, the oblate systems, they increase in fraction and prominence, which is a nice sanity check, because in the real universe, we do observe lots and lots of star-forming disks at lower redshifts. So this is nice to see this rise in the oblate fraction towards low redshift. So now we get to cosmic origins, which I'm very excited about, because as a NASA Hubble Fellow, I'm supposed to try to answer the same kind of question that the NASA Cosmic Origins Division is supposed to answer. And that is, how did we get here? So here's my take on this. Many people have shown that at high redshift, the stellar masses of Milky Way like progenitors are going to be roughly 10 to the 9 to 10 to the 10, say at redshift 2. And I just showed you that in the same mass redshift range, redshift 2, stellar mass 10 to the 9 to 9.5 or 10, we think that we're seeing a large population of elongated galaxies. And so you put these two things together, I'm pretty sure it implies that our Milky Way itself may have gone through an elongated phase itself. And now the question is, where do we go from here to kind of test this? And so I'll kind of skip through or step through a few possible angles for future work, starting with the most exciting, in my opinion, which is galactic archaeology. So I've talked to some people who have pointed me to some exciting work where the motions of stars in the stellar halo today suggest that the Milky Way had a radially biased merger with something called the Gaia Sausage Enceladus galaxy at redshift 2. And when that happened, the Milky Way got very triaxial, very elongated. So what a coincidence that we, with JWST and Hubble, are also observing high elongated fractions at redshift 2. So can we make this connection more directly in the future? I think that remains to be seen. Something else that I think will be exciting in the next few years is the Roman Space Telescope will launch. And in a single pointing, it will observe 100 Hubble deep fields at once. And so I think we'll be able to use Roman to identify many more of these elongated galaxies. And I'm trying to make this a really cool new science case for Roman, where with all these elongated galaxies in the Roman deep fields, we can actually revisit my 2019 paper and properly look for intrinsic alignment and clustering signals over huge areas of the sky. So that's going to be very exciting. Another open question is, can we use imaging and visual classifications alone to distinguish for any individual galaxy? Is it an oblate system, a prolate system, something in between, or so on? Dust is going to be very important. Bene and I have been talking about this. And the reason for this is that prolate galaxies have two short axes, and they're likely to be observed edge-on. But a prolate galaxy observed edge-on has a small path length because of its short axis along the line of sight. So it may have less dust reddening compared to an edge-on circular disk. So this is going to be maybe an interesting or fruitful avenue for future work. But I would argue that the most important thing in the future is going to be to constrain the kinematics of these systems to really settle the debate for individual galaxies. What is their nature in 3D? And not just gas kinematics, but really, thinking big, the stellar kinematics. So let me start with some thoughts on the gas kinematics. So there's already been lots and lots of very exciting work from IFU surveys like KMOS 3D, which have detected spatially resolved H-alpha emission lines across the face of many high redshift star-forming galaxies. Here's a nice star-forming main sequence diagram with some of these nice rotating ionized gas disks, velocity fields along the star-forming main sequence at redshift 2. It's very exciting, but typically these constraints are for the more massive end, above 10 to the 10 solar masses, redshift 1 and 2, and so on. And there's already indications from these surveys that as you go towards lower masses, so towards bluer colors in this diagram, and towards higher redshift, towards the right in this diagram, the fraction of galaxies that are lower mass or higher redshift that have clear signatures of rotating ionized gas disks drops dramatically. And in fact, for some of the lowest mass spins here, we don't have the statistics or the data quality to really definitively say much. This is going to change. I mean, it's already kind of changing because JWST is revolutionizing our ability to detect these rest frame optical emission lines out to very high redshift. And in fact, there's a paper last year by de Graaf et al. Who show very convincingly and nicely that JWST is going to be able to detect and constrain gas kinematics from like H-alpha emission lines, for example, down to very low masses and very high redshifts. And so we're going to start to build up more and more samples of this and comment on the incidence of rotating gas disks in high redshift low mass galaxies. But as exciting as this is, gas kinematics alone is never going to be a smoking gun. Okay, it's only ever going to provide you with some kind of statistical constraints on the 3D geometry of the stars. So for example, you could compare the gas kinematics versus the axis ratios in terms of correlations, or you can look for like kinematic photometric misalignments. And we're doing some of this stuff with Raymond Simons and Arnav Shah and Steve Finkelstein. But we need to go beyond the gas kinematics. We have to think beyond that. And we have to actually think about, in my opinion, the stellar kinematics, which is really going to be the smoking gun. And this is really cool because some of these simulations that are high resolution, where these elongated galaxies are seen, they suggest that the stellar kinematics is going to be completely different in these elongated systems compared to like edge-on rotating circular disks. So we already know that if you have an axisymmetric disk, then the stars are going to be on circular orbits about the center of the disk. But when you have these prolate or triaxial systems forming along these dark matter filaments, then you might actually end up with stars being on highly elongated, radially biased box orbits, elongated along the long axis of the galaxy. And so this is exciting because it says that maybe we have a way to, for individual galaxies, actually like constrain the 3D geometry, because these oblate, prolate, and triaxial systems, in terms of the stars, may leave unique signatures on the line of sight stellar velocity field. So you can actually ask for individual galaxies like this one, is it an edge-on circular disk or an edge-on oval disk or an edge-on cigar? Is it dynamically stable? Are there mergers with these little knots around it? What is going on with these kinds of individual systems? The problem, of course, is you have to detect a stellar continuum and then resolve redshifted stellar absorption features with high signal-to-noise ratio. So you can then fit stellar population models and look for velocity signatures. And the problem is compounded because these galaxies are very faint. They're very small, of order like 0.1 arc seconds or smaller. And then the simulations where these galaxies are seen, these elongated galaxies in simulations, they tend to predict rotational velocities and stellar velocity dispersions of order 60 kilometers per second or even less, depending on what mass regime and epoch you're looking at. So it's very challenging, but you can start to get a handle on some of the stuff, and people have tried. So the simplest thing you can imagine doing is you look for one of these elongated systems, and then as James Lowenthal, David Koo et al. Did in 2009, you just put a slit on it, aligned with the long axis, and then you look for signatures of velocity gradients in the stars. So in this example case, which they call the hot dog galaxy, they detected multiple stellar absorption features corresponding to redshift 2.8. But when they then checked if there was a velocity offset along the long axis in these stellar features, these absorption features, the velocities, they showed that they did not find any velocity gradient along the long axis, and they concluded this may be evidence that this is not part of an edge-on rotating disk, even though it looks elongated, and instead maybe it's a truly linear, perhaps filamentary source. And we don't really have a good consensus of the kinematics of these kinds of objects, especially at lower masses and higher redshifts. This is one of the brighter and larger ones. And this kind of slit spectroscopy itself is never going to be super convincing either, unfortunately. And the way I like to introduce that is by reminding everyone that the 3D geometry of local giant ellipticals was debated for decades. Go back to papers in the 1970s, and they were debating, are these actually just pancakes that you're seeing face on, or are they truly 3D, round in 3D? And they debated this because they didn't have spatially resolved kinematics information on the stars from IFU surveys. And it's only when those surveys became available and that stellar kinematics constraints became available that kind of more consistent pictures started to emerge about, for example, maybe the most massive ellipticals are truly round in 3D, and or slightly triaxial, and then maybe the lower mass ellipticals, the fast rotators, are maybe an extension of the S0s, more oblate. And so what we really need in the future is spatially resolved kinematic information on the stars, velocity fields with IFUs. And then you can use things like stellar kinemetry to kind of understand, decompose or fit the observed velocity fields with like the sum of different Fourier components. And you can do this kind of stuff also for the gas, which I've done for the most massive local ellipticals as part of the massive survey in the past. So this is going to be exciting if we can do it in the future. And an even more important, I think, but challenging thing to do is to do Schwarzschild dynamical modeling, where you actually try to fit the different types of stellar orbits that contribute, when averaged over long time scales, that contribute to the observed image of the galaxy, as well as the observed velocity field of the galaxy. So fortunately, this is going to be possible in the next 10 years with the extremely large telescopes, many of which are going to have, well, actually all of which are going to have the spectral resolution and wavelength coverage and spatial resolution with adaptive optics needed to do this kind of IFU stellar kinematics survey type stuff for higher redshift systems, including these elongated ones. But these ELTs at the end of the day are still going to be under the atmosphere. And so they're going to have limited sensitivity. And even with AO, they may not reach optimal resolution. And of course, they're going to be limited in their coverage of UV and IR wavelengths. So that brings us towards the end of my talk, which is what can habitable worlds do in the future? So as everyone may know, in the Astro 2020 Decadal Survey, one of the recommendations was for a large ultraviolet optical near-infrared telescope, which among other things would address cosmic ecosystems, which is directly related to this kind of stuff that I've been talking about on trying to understand how galaxies develop their 3D shapes over time, including galaxies like our own Milky Way. And so as part of this great observatory maturation program recommended by the Decadal Survey, the first telescope should be some kind of 6-meter UV optical near-infrared telescope that merges the best of LUVOIR and HabEx. And so if we can assume that habitable worlds will have some version of the high definition imager, for example, proposed for LUVOIR, then I think where habitable worlds will really shine in the era of the ELTs is in its ability to get very high resolution optical and UV imaging of the high redshift universe. So, and in particular, I think coming up, planning these habitable worlds deep field surveys like we've been doing with Hubble and now JWST. And in some of these deep fields, we may actually see some of these elongated galaxies, like the example shown in the LUVOIR final report. So here's an example of one of these redshift 2, 10 to the 9 solar mass galaxies that are star forming, Milky Way progenitor, as seen by HST, as seen by the ground-based European ELT. And then on the lower left, what something like habitable worlds might see. So you can see this is amazing. You can see like all these little H2 regions and UV clumps, and really at this redshift for this galaxy, you're probing with 100 parsec resolution in the rest UV and optical. And so, I'd be very excited to do things like pixel by pixel SED fitting, look for color gradients, maybe as signs of like ongoing or recent mergers. And the other thing is maybe you can look for these like UV bright clumps or star forming regions. Maybe their spatial distribution will tell you something about the underlying 3D geometry of the system. And not only will habitable worlds allow us to study like these redshift 2 Milky Way progenitors, but it's actually going to be able to probe much further down in mass out to higher redshift, as shown nicely in this figure from the LUVOIR final report. So the other thing that habitable worlds can do, of course, is spectroscopy, and in fact, multi-object spectroscopy. And I think in terms of the science that I've been talking about here, what habitable worlds will be able to do depends on what choices are made for its wavelength coverage. So in the LUVOIR final report, the LUMOS spectrograph would extend from the UV through the optical. And so if we can assume that habitable worlds will extend to the optical, well, then you can do the same kind of multi-object spectroscopy that like James Lowenthal and David Koo et al. Have been proposing and have done, and that we're actively working on now with larger existing archival data sets. And you can look for these elongated systems and look for rest UV absorption lines for galaxies at redshifts 1 to 6, and to see can you rule out convincingly velocity gradients. And/or you can use the micro shutters, which are relatively small in like an IFU mode almost, to kind of cover the face of a galaxy like this and look for velocity gradients in different directions. Although that would probably be the domain of the ELTs, this IFU mode spectroscopy, I think, for this kind of science. On the other hand, in the UV, the other cool thing to do, I think, will be to go to these redshift 1 elongated candidates. And there you can actually look for redshifted Lyman alpha emission for redshift 1 elongated systems, and maybe try to map that faint Lyman alpha emission out around these elongated things. Maybe look for signatures of outflows or even filaments that these galaxies may be embedded in. And you can cross-correlate the whatever Lyman alpha emission you detect in terms of its surface brightness and in terms of its kinematics, maybe, with the rest UV and optical 100 parsec scale resolved morphology of these systems from the imager on Habitable Worlds. So that's just a teaser of things that I could think of. There's many other ideas, of course, but I will stop there and just summarize by saying that I hope I've convinced you that there's this very important unsolved puzzle raised by Hubble and now still maintained by James Webb, that galaxies may start out elongated in 3D, and we won't have a real way to settle the debate until we get stellar kinematics, which we're working on with long slit spectroscopy and multi-slit spectroscopy now, but really we need IFU spectroscopy, which the ELTs will provide. And then Habitable Worlds, I think, is really going to change the game in terms of providing 100 parsec scale rest UV optical imaging to look at substructures within these galaxies, especially at lower redshifts, and then maybe also be able to detect faint Lyman alpha emission to look for signatures of outflows and filaments. So I will stop there and take questions. Thank you.
Thank you so much. That was awesome. I do, of course, have questions because galaxy morphology is sort of the red flag for me. So we'll absolutely have follow-up, but I want to open it up to the Zoom room first. Does anyone have a question to start off with? Otherwise, I'll jump in.
See a hand from Sankita. Go ahead and ask your question.
Hello, nice talk. And I was wondering if the number of these linear objects you're finding can be explained by interactions. So you have these tidal tails, and we kind of sort of know the interaction rates of galaxies. Yeah.
Yeah, that's a good question. I mean, our proposed explanation does involve interactions, mergers along filaments. But you're right that another interesting explanation, very closely related, is, yeah, you can have mergers and they'll preferentially lead tidal tails, maybe on similar elongated signatures. So I think that's another case where, yeah, maybe we'll need the spatially resolved kinematic information for the starlight to try to think of ways to distinguish between like just tidal features versus something happening preferentially along. This is telling us something about the cosmic web.
Dropped here for a minute for me. I have a question about, oh no, I see Alexander Le Rest.
Yeah, I had a question a bit similar actually. I didn't quite understand why galaxy interactions would have to occur along filaments for them to create those kind of morphology that you expect for them to be elongated and provide this explanation. Could you tell us more about why this has to happen along filaments?
So yeah, so you're right. So if you have galaxy mergers, in general, in projection, you might see the debris appear elongated. The merger, the filament connection comes in from these high resolution zoom in simulations where people have analyzed the 3D morphology of the stars and of the dark matter, and of the and then compared those, and in these simulations, the dark matter halos are also elongated, and we think that's because these dark matter halos are preferentially accreting matter in this high redshift, low mass regime along the dominant filament that they live in. So it's the current thinking from these high resolution simulations that these things are forming in filaments. But you're right, it'd be interesting to try to come up with a way to distinguish tidal features which would appear elongated in projection versus this scenario.
See any other questions? I had one, but I was going to wait until the room had finished theirs. Do you see any evidence for warps or truncation? Because those are very typical disk things. They're hard to spot because you have to be at the low surface brightness, but do you see like an exponential profile dropping off or a warp in the actual edge-on case?
Yeah, we haven't looked in detail yet, but we're starting to look into computing more non-parametric morphological parameters for these systems, maybe doing some kind of stacking analysis, and also fit the surface brightness profiles directly, as opposed to just like with like, for example, with elliptical isophotal fitting and get color gradients and things like that. So there's a lot more that can be done along those lines.
I have one more, but that's more of a like asking you for a comment. With the V over sigma, so looking for the disk effects, I remember reading that AO sort of takes out the lower surface brightness component, so you sort of skew yourself towards velocity dispersion because you're looking at the centers. Has that really been solved with the KMOS, or do you really need something like an IFU in space in order to solve that properly?
That's a good question. I haven't thought about that too much in detail. Be curious to hear your thoughts.
That's Carl Glazebrook's comment on the phi over sigma. There was a review of that. So he, there's a particular kind of review, but he wrote one in, I want to say 2016, but don't hold me to that. And he looked at the V over sigma relation, and that anything at redshift 1 was sort of suffering from the AO dimming of the low, or the weighting going wrong. Okay. So lots to do here. Some of those things look like some of the edge-ons that I've come to know and love in the nearby universe, but a lot of them really don't. So that was a fantastic talk about like the whole problem. So you laid it out fantastic. And clearly we need to go out and get more data and then see what then happens. Does anyone have other questions that's occurred to you in the meantime? Just opening it to the room again because I don't want to dominate. Okay, fantastic. Thank you so much for the talk. So that was a very fun topic, and I have plans for student projects now, so that's amazing.
Great. Thank
Thank
you.
you.
Yeah.
Thank you all for coming. We will have another one soon. Aaron is.
I think the next one is February 7th by Peter
Yep.
Baruzzi. And just to throw a few quick word to the end of the recording. So HWO is now looking for people to participate in various working group. If it might have come to your inbox, just look for it as a Google form to fill out. If not, I'm happy to forward you that. Just reach out to me. Also, there is a HWO related precursor science call. So the deadline for the proposal, I think, is March. If you're interested in applying, go right ahead. Okay, that's all I have. Okay, cool. Good. I'll see you all
Cool.
in 2 weeks then.
See
Take
you
care.
2 weeks
Bye.
time.
Thanks again.
Thank you.
Thanks
Thank you
again.
for all for coming. And thank you.